Good afternoon to you viewers and subscribers. Welcome back to the channel. Welcome back to another video. In my last video, I've shown you how to calculate the minimum reinforcement for a column. In this week's video, I'm going to delve into a little bit of reinforced column design or reinforced concrete column design. So there are two different methods you can use to calculate or to design a column. You can place some amount of reinforcements in the column and then use the design formula to calculate how much loads or the load capacity of that column. The second method is you can just simply design the column to carry a particular loads. All right. So in this week's video, I'm going to show you a column that I have on one of my drawings and how I calculate the load capacity or the nominal load or the amount of load that column can carry based on the amount of reinforcement. So stick and stay to the video. And as usual, I want you to watch the video until the end. And in the events, if there are any ads that show up in the video while you're watching the video, watch some of the ads as well. All right? Stay tuned. In order to design the column, I turn to the ACI code 318, page 38. All right? So on the right here, you can see the commentary. The basic requirement for strength design may be expressed as follows. The design strength must be greater than or equal to the required strength. So you observe these criterion here. We have 5 PN is greater or equal to PU, and that is for column. And we have here 5 MN, which is greater or equal to MU, that is for reinforced concrete beams. And then we have 5 VN, which is greater or equal to VU, and that's for shear in beams or reinforced concrete beams. But since we are focusing on column design, we are going to work with this criteria here, which is 5 PN greater or equal to PU. Your 5 PN is the nominal loads or the load capacity of the column. Your PU is the required strength or your ultimate load, and it is always the factored load. So we have PU, which will equal to 1.2 dead plus 1.6 live. So what we as engineer does, we factor our live load by 1.6 and we factor our dead load by 1.2. So this is a criteria that we must establish. All right? To design our column, we turn to the ACI code again, page 133, and I'm gonna show you the design equation that we're gonna use to calculate the amount of reinforcement that this column can carry based on the load. So we have two criteria here. We have one for spiral and we have one for tie. So since we are using non-compressed members with tie reinforcement, we are going to use this formula here or this equation here to calculate the maximum load capacity of the column. So this is the formula here that we are going to use based on the ACI code. So let's get into the calculation. All right. The column that I'm going to design or show you how to calculate the maximum load capacity is this column here. This is a column that I have on one of my plans. So if you should observe, this column have a dimension of 1 foot 2 inches by 1 foot 2 inches, which is 14 inches by 14 inches. So as I've shown you in the last video, the first thing you want to do is to calculate the cross-sectional area, or the gross cross-sectional area. So the gross cross-sectional area of this column, it is going to be 14 inches times 14 inches, which gives us 196 square inch. The second thing I want you to observe, viewers and subscribers, is the amount of reinforcement that is placed inside this column. So if you can count with me, we have 1, 2, 3 here, 1, 2, 3 here. So we have 6 reinforcing bars that is placed in this reinforced concrete column. And if you observe the cutout here, it is number 6 or 19 millimeter in diameter, 3/4 inch MSB as vertical bar. So this column here has a reinforcement of 6 3/4 inch bar. So we need to calculate the area of steel that is placed in this reinforced concrete column. So the area of steel is going to be 6 times 0.44 inch square. As I've shown you in my last video, that the area for a number 6 bar is 0.44 inch square. So let me turn to the code to show you just that. So this is a code, this is the table here where you can get, or you can obtain the values for your square area based on the size bar. So we are using a number 6 bars, and if we come across here to the nominal area in inch square, we have 0.44 inch square. So number 6 bar, the area of that bar, the cross-sectional area of that bar is 0.44 inch square. So it is going to be 6 times 0.44 inch square, and that works out to be 2.64 square inch. So the area of reinforcement for this reinforced concrete column is 2.64 square inch, and the cross-sectional area is 196 square inch. Viewers and subscribers, so this is the actual calculation that I want to bring to your attention, and it is how to calculate the maximum load capacity for a reinforced concrete column. Right, so as I mentioned to you before, we have to obtain the phi pn greater than or equal to pu for a column. We must establish that. Okay, and then we have our rho g, which is equal to the area of steel divided by the gross area. So this is the equation here. I've shown you the equation already based on the code, right? And I'm going to show you now what the different components of this equation mean. So we have phi pn, which is the nominal load or the load capacity. We have Fc prime, right? Fc prime, which is the compressive strength of concrete. We have our gross area, Ag, which is our gross area. We have AST, which is the area of steel, and we have Fy, which is the yield stress of steel. So our design parameters, we have phi, which is equal to 0.65 for tie reinforcement. So let me go back to the code again and show you. So if you observe what the code is saying here, section C.9.3.5 in chapter 22, phi shall be 0.65 for flexure, compression, shear, and bearing for structural plain concrete. So since we are doing a column, and we know that column is a compression member that carries axial loading, we're going to use our phi as 0.65 for tie, right? So we're going to use a compressive strength of concrete, which is 2,175 psi. This is equivalent to a 1-2-4 concrete mix, and we have our gross area, which I have shown you the calculation already, which comes up to be 196 inch square, and we are going to use a yield stress of steel, which is 60,000 pounds per square inch or PSI, and our area of steel, which I've just shown you the calculation again, which is 2.64 inch square. So simply what we do is just plug these values into the equation. So we have phi Pn, which is equal to 0.8 times 0.65 open bracket 0.85 times 2175 psi. We have open bracket again 196 inch square minus 2.64 inch square plus 2.64 inch square times 60,000 psi. And we work that down into the equation. So we have 5pn, which is where you times 0.8 times 0.65, we are getting a value of 0.52. So simply we just work this down into the equation. So when we come down to the equation now, we have 5pn, which is equal to 344,286.64 pounds. Okay, and then we want to find our pn. So since phi is 0.65, we design 344,286.64 pounds by 0.65, and the result of that is 529,671.75 pounds. So we can see that the load capacity for the column is 529,672 pounds. All right. So this column, let me go back to so this column can carry approximately 530,000 pounds. All right. So that is how I calculate the load capacity for the column. I just simply place these values in the design equation, and I'm getting a result of approximately 530,000 pounds. All right. So that is it for this video. This is only a small calculation of a column. As I said to you before, there are two different ways how you can calculate the column capacity. You can design the column to carry a particular load, which is a much more tedious exercise. This is only a short way of how to determine how much load a column can carry. Okay, but if you want to go deep into the calculation, you have to know how much live load as against how much dead loads that your column is going to carry, and you use this design formula here to calculate the area of steel, and you divide the area of steel by the area of steel that you want to use, and that is how you get how many steel or how much steel that you have to place in that column to carry the load. And one more thing I want to point out to you viewers and subscribers before I leave this video is that this design formula is not a simple formula to use. Okay? It is a very tedious formula to use when you are designing for the area of steel. If you observe the formula, you can see AST is in the formula two times. You have AG here, gross area, minus the area of steel, and outside the bracket we have plus area of steel plus the yield stress of steel. To calculate the area of steel, to make area of steel the subject of this formula, can be very, very tricky. And there's also one other thing I want to point out too before I leave. You do have engineering software that you can use to input these values into the software, and it does give you the results. But any engineer will tell you that to do and calculation is the best way how to design. I mean, some designs are very, very tedious and you do not want to use and calculation. You can use engineering software. I use engineering software at my work. I do not really use hand calculation, but hand calculation is very good. If you cannot use hand calculation, you're not going to be able to interpret the result of the engineering design program. Okay, and use and some amount of that and some inputs that you have to place in that software, you have to calculate some of those inputs to go into the engineering software. So some people might look at it and who are engineers and say they don't bother use on calculation. They have engineering software where they can just put the values in and you get the result. But on calculation is a very useful skill to have as engineer. Okay, so that is it for this video. I hope you enjoyed the video. If you have any questions, shoot me a question. You can leave the question in the comment section of this video, and I will be more than happy to answer your question. Thank you. Enough respect.